Now let's talk about an application of radioactivity when we discuss how you can radiodate samples. Here we'll talk about doing radiocarbon dating. This is often used to determine the age of an organic sample. We'll begin by reviewing the isotopes of carbon. There are 3 isotopes of carbon, and the first one, probably the most well-known and the most important one for us in Gen Chem, is carbon-12. This is a stable isotope that's present in 99% abundance. Right, so 99% of all carbon atoms on planet Earth are of the carbon-12 variety. However, about 1% of the carbon atoms on planet Earth are of the carbon-13 variety, right? So it has 1 additional neutron. This is also a stable isotope of carbon, and this is a pretty important isotope of carbon in the field of organic chemistry, because this isotope of carbon can help give you information about an organic molecule's structure. You'll learn about that a lot more if you have to take organic chemistry. The third isotope of carbon, which is something we're going to focus on here in this video, is the isotope carbon-14. Now, this isotope is only present in a fairly small abundance. Its natural abundance is somewhere around 10 to the minus 10%. But this isotope is unstable and undergoes a beta decay process, and so that will make any sample that contains carbon slightly radioactive. It will give off beta particles, and you can determine the number of beta particles that are being emitted to help give you information about the age of a sample. Now, in all living things, carbon is going to be continuously replenished, right? Because let's say that for like living animals, they consume food, and as they consume food, right, they're going to synthesize the food, metabolize it, and it goes into their body, and that's going to be continuously replenishing the carbon that makes up their body. And because carbon is continuously being replenished, all 3 of these isotopes of carbon will be present at constant levels. In plant life, the same sort of thing happens, except in plant life, the process that you're going to be undergoing is photosynthesis, where you combine CO2 and water to make cellulose, which then gives plants their structure. But because you're pulling CO2 out of the air and it's being continuously replenished in the plant life, again, the levels of all 3 of these isotopes of carbon will be constant as long as the plant is living. Now, after a living thing dies, carbon is no longer being replenished, right? After an animal dies, it's no longer eating food, so there's no new source for carbon to come in. After a plant dies, right, it's not going to be undergoing photosynthesis anymore, and so there's going to be no new carbon coming into the plant. So carbon is no longer being replenished, and effectively what that does is it starts a stopwatch. And the stopwatch starts because carbon-14 in the sample will be decaying, and as it decays, the abundance of carbon-14 goes down. Its radioactivity goes down over time. And as a result, you can measure what the radioactivity of the sample is after many, many, many years and compare it to what the expected initial amount of radioactivity would be. And by comparing those 2 values and using first-order kinetics, you can determine the age of a sample. That's how you're able to radiocarbon date samples that are found on, let's say, like archaeological expeditions. So let's go ahead and work through an example problem here. Here we're told that a 30-gram sample of carbon that was discovered on an archaeological dig was determined to have a radioactivity of 3.9 times 10 to the 5th becquerel. And that's just measured experimentally using equipment in a lab like maybe a Geiger counter. Now, for comparison, the radioactivity of a 30-gram fresh sample of carbon would be 1.7 times 10 to the 6th becquerel. We're told that the half-life of carbon-14 is 5,370 years, and from this we're going to determine how old this sample of carbon is. Effectively, what we're being asked here is, for how long has the carbon-14 in this sample been decaying? And when a question asks you how long does something take, you want to think about using an integrated rate law. Again, because all nuclear decay processes occur on first-order kinetics, we're going to write the first-order integrated rate law, which is going to say that the new amount of carbon-14 will be equal to the initial amount of carbon-14 times e to the minus kt. Now, let's think about how we're going to solve this problem. I've mentioned previously that in first-order kinetics, because of the way that the units cancel out, you can use whatever units you want for concentration, as long as you're consistent. So you can use units of molarity, you could use units of grams, which we saw in our previous video. You could even use units of radioactivity, as long as both this and this are expressed in units of becquerel, because when you go to solve this problem for T, the units are going to cancel out. So just be consistent and it's all good. With that in mind, let's go ahead and start solving this equation for T. You could divide both sides of the equation by the initial concentration of carbon-14, and then next we have to get T out of the exponential, so you could take the natural log of both sides of the equation. Now notice that this ratio here, the new amount of carbon-14 over the initial amount of carbon-14, is unitless as long as you're consistent with the units. And that's again why we could just use becquerel for both of these, because the becquerels cancel out and it's totally unitless, right? And the natural log, the argument of a natural log will always be unitless as well, right? So this again kind of speaks to why we don't really care about what units we use here. You could use molarity, you could use moles, you could use grams, you could use becquerel, as long as you're consistent because the units are canceling out. The last thing that we have to do to isolate T is to divide both sides by negative K. That's going to give us that the age of the sample will be negative the natural log of the new amount of carbon-14 over the initial amount of carbon-14 divided by K. Now we need to know the value of K, because that's really the only thing that we're missing here. And so to find the value of K, we look for other information that's given to us in the problem, right? We recognize that we're given the half-life, and therefore now we can use the half-life to get the value of K. And I'm going to go ahead and kind of shift everything up here a little bit to get a little bit more space. All right, remember that T1/2 is equal to the ln of 2 over K. And so you can cross multiply to solve this for K. K is equal to the ln of 2 over T1/2. Now, you were told that the half-life for carbon-14 is 5,370 years. So we'll plug that in here. And when you plug all of this into your calculator, you're going to find that the rate constant for the beta decay of carbon-14 is 1.29 times 10 to the minus 4, and the units are years to the minus 1. Lastly, we're going to plug this into the integrated rate law and solve for time. So what we have here is that T will be equal to the negative natural log of the new amount of carbon-14, or that's the new radioactivity of our sample. That was given as 3.9 times 10 to the 5th becquerel, divided by the initial radioactivity of the sample, right? So we found that in a fresh sample of the same size, the radioactivity was 1.7 times 10 to the 6th becquerel. And then we divide that by the rate constant, which we now know to be 1.29 times 10 to the minus 4 years to the minus 1. When you go ahead and plug all of this into your calculator, the final answer that you're going to get is going to be in units of years, right? Because you have 1 over years. The becquerels cancel out, right? We're consistent with the units, so again, it doesn't matter what units you used for the concentration of carbon-14. All right, everything gets plugged into your calculator, and the number that you're going to get is going to be 11,413 years. And so that is how you're able to determine the age of the sample. This sample is 11,000 years old. All right, that brings us to the end of our discussion of radio dating. And up next, what we're going to do is talk about the thermodynamic stability of the nucleus.